So in this session, we're going to do integration, and integration is simply the reverse of differentiation. The first rule that you did in 1100 is that whenever you're integrating something, we simply increase the power by 1. This is applicable to linear functions and polynomials, and divide by the new power, then add a c. If there are no limits, if there are limits involved, let's say you had a b and an a, integrating a function will give you the integral. You would evaluate the integral both at a and b, then find the difference. This would have been f of b minus f of a to give you the area of that particular curve between the numbers b and a. Yeah, this is like the basic rule. Now let's talk about the methods of integration. We'll start with the first one, the algebraic substitution. So I'll give you some examples from here. This is just the same thing as u substitution. Yeah, so method 1 is substitution, or rather we just say it's reverse chain rule. It's more like chain rule, but then under integration. So these are cases that we're going to look at under substitution. It mostly applies if you're able to see a section which has a weird power or a very big power, or rather you see something that has either a function and its own derivative outside. For example, you're seeing here to say if you differentiate this, you get this guy which is outside. At least they look a little bit alike. Yeah, something like this, where there is it's like chain rule, like I said. Remember when you say the integral of the derivative, when you say the derivative of sine, we used to say when you differentiate sine, you get cos, right? Then there's some later on you said when you differentiate sine of something, the answer is going to be u prime cos of that thing. So the same applies when we're integrating. The only difference is that this time around we're going to be having the derivative put as a denominator. So when we say we're integrating anything, let's say sine of u, this is just going to be the same as negative cos u over u, then plus c. Remember, the derivative of cos is sine, negative sine. That's what you have. So meaning the integral of sine should give us what? Should give us negative cos. Yeah, so this is the only time you get to use u substitution, is when the power is weird, or when you see that what's inside if a particular function is a derivative, its derivative is the guy which is outside. Yeah, so look at some examples. The first one, I'll give you something that looks like this: 2x. There's x squared, let's say plus 3. This is to the power 5. Then we have dx. So we're going to let the part that has a bigger power be our u. So this is also called u substitution. So we let u be equal to the x squared plus the 3. So du dx is just going to be your 2x. And the function now, the integral changes, it becomes 2x, u to the power 5, then dx. We make dx the subject of the formula from this part. That's going to be dx is equivalent to du over 2x. This now becomes 2x u to the power 5. Then we put du over 2x. This is just now going to be, this cancels with that, the integral of 1 u to the power 5 du. This now changes and becomes u to the power negative 5 du. We apply the normal rule because now we are integrating with respect to u. This isn't just like a polynomial, except the power is negative 5. We increase the power by 1, it becomes u to the power negative 4, divide by the new power. It was indefinite because there were no limits, so we add a c at the end and replace the u with our x squared plus 5. This is the power negative 4 over negative 4, then plus a c. So these are times when we use integration by substitution or algebraic substitution. Let me give you another instance where you have trig ratios. if you have, let's say, sine x, and let's say cos to the power 4 x dx. So in this case, you let the part or the function which has a bigger power be your u. So let u be equal to cos x. The derivative is simply going to be negative sine. So dx is the same as du negative sine x. This is sine x, then u to the power 4 du negative sine x. We cancel the sine. This is just going to be u. This is du. Then from here we say u to the power 5 over 5 plus c. We change this back to cos to the power 5 over 5 plus c. This is cos negative cos x to the power 5 over 5 plus c. So this is what you get as your outcome. So you let the inside part be equal to u, so that you get the derivative. The derivative here is just going to be a 3, meaning your dx is just du over 3. So you can say the integral of sine u, then du over 3. This is the same as 1 over 3, the integral of sine u, then du. The integral of sine is negative cos. So say negative cos u, then plus a c, negative 1 over 3. Then here we put our u to be cos 3x is it plus 1 and plus a c. Yeah, so this is basically when we apply u substitution. The next method, so method 2, is integration by parts. So by parts works the same way that product rule under differentiation works. It's only used whenever you have two functions multiplying each other and they have nothing in common, or they're not related or whatsoever. So the formula that we're going to use is something that looks like this. We say whenever you have the derivative of something that you're interested in, we can always integrate using this same formula here to say the integral of v, then we say u prime is equal to v times u, then integrate the u and the v prime. Yeah, so this is the formula, or whichever one you decide to use. The implication is really the same because it's just different ways of how we write the formula, but the meaning is the same. Yeah, so I'll give you examples here that you can just understand the concept from. So if I give you, let's say, x ln x, then dx, the choices of your v and your u prime depends on how you want the expression to be. We need to be making it simpler as we start solving. So if you decide to choose, like in this case, to choose your v to be your x and your u prime to be your ln x, it means if you're looking for v prime, you differentiate the x, and if you're looking for u, you have to integrate the u prime. In this case, we cannot integrate ln of x. We don't have an answer to that. So would rather change or rather switch our choices and make this to be our ln x, because we know the derivative of ln x is just integrate x, differentiate x, that's a 1 over the original thing. That's a rule, right? If you have y is equal to ln u, the derivative is just the same as u prime over u. No wonder we're saying it's 1 over x. Here we have x. The integral of x is x squared over 2. This is easy because when we replace in the substitution, in the formula, the last part won't be hard to integrate because we have x ln x dx is equal to vu, which is just x squared over 2 ln x, minus u times v prime, x squared over 2 times 1 over x dx. This here is going to be the same as x ln x dx is equal to x squared over 2, then ln x minus, this is just the integral of x over 2 dx. And this is just going to be the same as x squared over 2 ln x minus half integral of x dx. Then this will just become minus, this is a minus here. The integral of x is just x squared over 2. We add a c because this was an indefinite integral. There were no limits given. So you have x squared over 2 ln x minus x squared over 4, then plus a c. So this is what we get according to the by parts method as the integral of x ln x. Yeah, so it has to be becoming simpler as you are working it. If your thing gets very complex, it simply means you're doing something wrong, or you just have to reverse your choices. Let me give you something that's a little bit interesting. If you are given something like this, or something that looks like this, yeah, so do these two. So choose this part here to be our v. So if v is ex and u prime is sine x, the derivative here is 2ex according to the rules. If you differentiate e to the power x, it's 2 itself. Then u, when you integrate sine, you get negative cos. So according to the formula, we already have our ex sine x dx. Vu, we multiply these two, it will be negative e to the power x cos x minus the integral of u prime of our u times our v prime. That's going to be negative ex, then we have cos x dx. This becomes ex sine x dx is equal to negative ex cos x plus integral of ex then cos x dx. So when you reach at this stage, you notice that the part you are having on the left, that should be part of the answer, which is supposed to be easy to integrate, should also be integrated using the same integration by parts. So I'm going to get this part and integrate it again, the one that I've indicated here in yellow. So we get our e to the power x cos x dx is going to be, when you use by parts, I'll just choose my v to be e and my u prime to be cos x. So we're going to get, this is going to be u is sine, we're going to get ex sine x minus, we're getting ex and sine x. That's what you are getting. So we'll take this part and replace it there. So we're going to substitute it there because that's the integral of this, right? So I'm going to write it. The first part is 2 in white. Ex then sine x dx is equal to negative ex cos x plus the integral of this part is the one I highlighted here. So I'll put it in green so that you just see it. This is going to be ex sine x minus e, the integral of ex then sine x dx. So you see that it has become a repeated integral because the e sine x is appearing on both sides. So we take this on the other side. That will be the integral of ex then sine x dx plus the integral of ex sine x dx to be equal to negative ex then cos x plus ex then sine x. We add this, we get a 2 integral of ex then sine x dx. This is equal to negative ex cos x plus ex sine x. We divide both sides by the 2. So the final expression is that the integral of ex sine x dx is the same as 1 over 2 negative ex cos x plus ex sine x then plus a c. So this is how we handle such, and you can attempt this other expression. You can try this. It's the same thing as well. It's going to be a repeated type of integral, so you can attempt this as a task to just see if you're following through. It will be the same. The other example that I wanted us to do is EX then ln X. So you have EX, then you have ln X dx. So here we'll choose our V to be our ln X, so that the V prime can be gotten easily as 1 over X. Then this side you're going to have our U prime, which is just EX, the integral, whose integral is also the same thing. This is again EX, so if you replace, that's EX ln X minus the integral of EX, then we have 1 over X dx. So to evaluate this, we are also going to use by parts, because we have EX and 1 over X. So choose our V to be EX, and we choose our U prime to be 1 over X, so that we can let our V prime be EX, and our U, whenever you integrate something where the numerator is the derivative of the denominator, the answer is just ln that denominator that you have. Yeah, so this is going to give us something repeating as well. EX ln X dx is equal to EX ln X minus the integral of this is supposed to be VU, these two, so it's EX then ln X minus the integral of this guy and that guy, that's EX then ln X again. Yeah, so this is just going to give us EX ln X dx. This gives us EX ln X minus EX then ln X plus EX then ln X dx. So in this particular case, you notice that this part here cancels. This part here cancels. We're going to have EX then ln X dx is equal to this gives us what we call a special function, because it's going to be repeating and getting advanced. So we're going to see that we get our ln EX then ln X then dx. So this is what we call an exponential special case. We just write it like this, then plus a C, but it's okay for you to not learn this. So to apply what you've done or what we've covered, I would like you to just attempt something that's on your tutorial sheet. So you can just try this and show me this on WhatsApp. Just attempt to solve this. E to the power negative x then dx. Remember that whenever you are differentiating e to the power anything is the derivative of that thing, then eu. If you are integrating this, so this is when you are differentiating it, you get this part if you are getting the derivative. But if you are differentiating it, if you are integrating it, it's going to be eu, then u, then plus a c. This is what you get, the derivative of the u, whatever is on the power of e. Yeah, so try this using by parts. Okay, so there are some portions apart from what we've been doing where we need standard formulas to use. Yeah, so please make sure you show me this on WhatsApp. Before we go to the next part, we have to discuss a few formulas which are called reduction formulas. We'll start with a case where you have something raised to the power n. You have something that looks like this. Yeah, so that you are able now to evaluate anything that will be, let's say, x squared plus 1. Let's say they put a 3 there. You'll be able to get it. The same applies to if you'll be able to get the reduction formula of sine, meaning you'll be able to solve anything they give you in terms of sine to the power 4, for instance. Yeah, so these are standard things that we have to learn. So I'll teach you how to derive, but you don't actually have to always derive them. You can just like master them and use them whenever they give you a question. Yeah, so n can be a constant. It doesn't matter whether it's negative or positive. That's what we have for the first case here. So we have case 1. We want the reduction formula of x squared plus 1 to the power n dx. The first thing you do is try to apply u substitution. You're going to let u be equal to u is equal to x squared plus 1. Then you're going to have du dx is equal to 2x. This then becomes u to the power n, and from here you're already familiar with how we make dx the subject. This is 2x, so this is just going to be du over 2x. So that's the first thing, is that whenever you have this expression here, the integral of x2 plus 1 to the power n, the answer is the same as the integral of your u to the power n over 2x. Then you have what? You have dx. Yeah, so again we have to integrate this part. So whenever they want us to get the reduction formula of something, in this case we're going to use by parts. We're going to choose this whole thing to be our v and the dx to be our u prime, so that we can differentiate this using chain rule. When you're differentiating using chain rule, we say bring down the power, that's going to be n, differentiate what's inside, that's 2x. Then write back what you have and reduce the power by 1. Then for this part, this is just like a 1 here, right? So if you are integrating it, it's going to give you x. So that we can now say, it's supposed to be this times this guy, that's going to be x. Then you have x squared 1 to the power n. Then you say the integral of this x times what we're having there, that's going to be 2x squared and n. You see x squared, then plus 1 to the power n minus 1 dx. So you see that what we've gotten has x squared. This is what we have. We can factorize the 2n out because these are just constants. The integral of x squared, then we have x squared plus 1 n minus 1. Then from this part here, so you notice that we have an x squared outside here, and this x squared is almost the same like the part which is inside, except there is no 1. So we're going to include a 1, so this just changes and becomes, I'll rewrite this whole thing, the integral of x squared plus 1 to the power n dx is equal to x and x plus 1 n. Then you have a 2n. This is the integral of x squared. I'm going to add a 1 and also subtract a 1 so that you see that nothing has changed. Then this is x squared plus 1, then negative this x minus 1. That's what we're getting. Then from here we're going to multiply the part which is on the right. We're going to have x squared plus 1 n minus 2n, waiting for the integral of these guys inside. So the integral of, we are now going to multiply this part. We multiply this part, this whole thing in brackets here, multiply by, I multiply it with this. The powers here, the power here is 1, the power here is n minus 1. So 1 plus n minus 1 is just n. This is going to be x squared plus 1. Then you have an n minus, when you multiply this by this guy here, which is just x squared plus 1, then n minus 1 dx. We distribute this negative with a 2n. It changes and becomes x squared plus 1 n minus 2n integral of x squared plus 1 n dx, plus we have a 2n integral of x squared plus 1 n minus 1 dx. So you're able to see that the power has decreased this side. So we're just saying this is almost similar to what we have, the original thing. So we call it in. This is also the same as in this side. Yeah, so this part here will just give you a plus a 2n whenever you have in minus 1. This is like the original case. Now subtract 1 from the power. So this is what we have. and we can just make in to be the subject of the formula. Take this on the other side. It will be 3 in is equal to x squared plus 1 n plus 2n and in minus 1. Yeah, so if we have this, we can divide by 3, then divide this whole thing by 3. Yeah, so it will give us, this is x, then x squared plus 1 to the power n. This gives us what? This gives us a 3 plus a 2n over 3. You have in minus 1. So this is like the general formula for our case. Yeah, this is what we're going to be using whenever we need to get anything in terms of us integrating what we were given initially. Yeah, so the general formula should have just been left here. We don't actually get to simplify it. We'll just leave it here. It explains everything with the I. So in an event where our n is equal to 2, we'll just use this expression here on top to get our answer. So we'll just have the following. If you have the integral of x squared plus 1 to the power 2 dx with respect to x, this is just going to be the same as I2, meaning where there's n, we are putting 2 in the whole expression. This is just going to be I2, which is the integral of x squared plus 1 to the power 2 dx is equal to, we say x, then you have x squared plus 1 to the power 2 minus a 4. The integral, this is just the same as the same thing again, which is x squared plus 1 to the power n. Then you're going to get this is dx, then plus this is 2n, the integral with this number reduced to 1. So that's just going to be the same as x squared, because this is minus 1. So we'll put our 2 there, 2 minus 1, that's just a 1. So we have x squared plus 1 dx. Yeah, so now we're going to get the following. This is already our x squared plus 1 to the power 2 dx. Yeah, this is still the same, x squared plus 1 to the power 2 minus a 4 integral x squared plus 1, the power is 2, and plus 2n. This is 2, okay. These are like terms, so we bring this on the other side. It's going to give us a 5, by the way. So it's 5 integral of x squared plus 1 the power 2 dx is equal to, we leave this x squared plus 1 the power 2 plus 2. Here there was n, it was 2, right? Remember those 2. It's an integral. Whenever we integrate this one, it's x to the power 3 over 3. This is just going to be x plus a c at the end. So this is just the integral of x squared plus 1 the power 2 is actually the same as x and x squared plus 1 squared. This is the same as a 4, right? So it will be 4x to the power 3 over 3, then you have a 4x plus a c. So that's what you get as the integral of an expression like this one. Yeah, this is how we get the reduction formula. Let me show you for sine, then I'll give you a task for cos. So what's the reduction formula for sine? How do we get it? So we have sine nx dx. So when we're looking for the reduction formula for sine, we're going to reduce the n. So we take the best case scenario that the n is an even number. So we're just going to call this in. This is in, this guy. So we're going to break down the sine into being sine x and sine n minus 1, then dx, so that we just get two portions. Yeah, so we're going to let the one that has a bigger power, which is sine n minus 1x, so that we can get our v prime as sine x. Then here we're going to look for the derivative of this guy here. So we're just saying u prime. Using chain rule says we bring down the power, that's n minus 1. Differentiate sine, the answer is cos. Then write back this minus a 1. This will be sine n minus 2x. Yeah, that's what we get. Then here you're going to have the v, which is the integral of sine, which gives us negative cos x. So we can now apply. Of course, we're using by parts. So this is going to be sine nx dx is the same as the v times the u, which is negative cos x. Then I have sine n minus 1 x. Then this side I'm having a minus sine times this. This is cos x, this is sine n minus 2 x dx. This is going to give us negative cos x. Then sine n minus 1 x. So we're going to have the sine times the sine n. This is only going to leave us with cos this sine n minus 1 again dx. This is what we're having. Cos x, then sine n minus 1 x. Yeah, so here the choices, the by parts we've done is using the one that says u, then v prime is equal to the vu, then you have v and u prime. That's the one we've used here. Yeah, so that's why here it's supposed to be cos, then cos times cos. That's a cos squared, then the negative and the negative become positive. So we can literally just factorize the n minus 1 outside. It leaves us with cos squared, then sine n minus 1, then dx. This is what we get. This is sine n x dx. Then from here we can take this part, because the n is going to affect everything. We can expand this part. So the main reason why we can expand it, because we see that the cos squared here can be replaced with sine, 1 minus sine, that identity for sine. Yeah, so this is going to be the integral of sine nx, then dx is equal to negative cos x, then sine n minus 1 x. Then this is going to be plus your n minus 1. This here is the same as 1 minus sine. Then you have sine n minus 1 x dx, or there should have been an x here because it's sine of something, right? So this is negative cos x, then sine n minus 1 x plus n minus 1, the integral of sine n minus 1 x dx, negative your sine, because the 2 and the 1 are going to give us what? If you're multiplying this, this is going to give us, is it n plus 1? Yeah, that's just supposed to give us what? A 2, right? If we take it back from here, or this is supposed to be a 2, yeah? Yeah, because we subtracted it, that's supposed to be a 2. This is now going to be n. Now it makes sense. Negative cos x sine n minus 1x. We can as well multiply everything with this because the integral is going to be distributed. Yeah, but to avoid all that, we're just going to leave it as it is. This is just the same as n minus 1 with this sign, because I want to separate them, but then the n minus 1 is everywhere. So to make life easy, we just write it as in, then this side again you have in minus 1. This is going to be minus n minus 1 with an in. Yeah, so this is what we get as the partial reduction formula for anything that has sign of something. Yeah, this can work. Yeah, so it means like if you are given, let me show you, you are given the integral of sine to the power 4. This can work because you can just put the 4 wherever there's n. It's negative cos x, then you say sine, you say 4 minus 1, that's a 3, right? X, this is just a 3, then this is just going to be sine 3x. Then you have yeah, dx minus, you have, that's a 3, Then this part again will give you the same thing that you had, which is sine to the power 4, because it's n, right? This was n. N is the original thing. Yeah. So now we can take the like things, take this back. It's going to give us a 4 because they're the same. This guy and this guy are the same. This is a negative 3, goes this side, they becomes a positive 4. This is just sine 4x, then dx. Our problem is to deal with this part here. That's a problem. So we're going to have negative cos x, then sine 3x minus 3. This part again, the sine 3x, will be solved using the reduction formula again. We do this part again using the same formula. So if I may use a different color here, we're using the same expression. So where there's n, now we're putting 3. That will be negative cos x sine 3x minus 3. We're putting the 3 wherever there was n. So this is going to be negative cos x sine, that's a 2 now, plus that's a 2 now. This is now going to be a 2 minus n minus 1, that's a 3. I3. And if you solve this part, because we're saying I3 is equal to what we've gotten there, which is negative cos x sine squared, then you have plus 2 I2, then minus n1, then you have I3. We can take this on the other side. This is a 2, that's going to be a 3, I3, negative cos x sine squared, then this is just plus 2 I2. So wherever there is this, we can replace with, if we divide by 3, divide with a 3. So it's negative cos x sine 3x minus the integral of this is just the negative cos x sine squared x plus 2I2 everything over 3. Yeah, so this is now going to become, remember there's a 4 this side, don't forget about the 4. There's a 4 I4. Yeah, so we're just trying to reduce the I, so there's a 4 I4. Yeah, this is just negative cos x sine 3x minus, or this is going to be now, there's a 3, there was a 3 that was waiting outside, there was a 3, this 3 can cancel with that 3, leaving us with a positive cos x sine squared minus 2I2. Again, you break it down using the I2. So our problem is that we shouldn't have any I on the right hand side by the time we're done solving. Yeah, so your final answer for the whole thing, the reduction formula, we're just saying it's going to be repeating itself over and over again. The final answer for reduction formula for anything that has to do with sine is just in is the same as negative 1 over n. Then we have cos x, this is sine n minus 1 x dx, then plus n minus 1 over n. Then we reduce what you have by 2. Yeah, this is just like the general formula for the reduction formula for sine. So maybe you can try to get sine 5x dx. So just try to get this, then show me on WhatsApp. So now that we've done this, I was just trying to recap on the laws. Partial fractions, we did this already. I was forwarded the video in the group. It shows how to decompose partial fractions, and the rule that we apply for partial fractions is whenever you see that the numerator is the derivative of the denominator, the rule here is just to say it's ln, the guy that you see down, then plus what? Plus that. No wonder we say if you're given something like tan, right? Yeah, tan. So like the integral of tan is the same as sine over cos, right? So this is just going to be negative ln cos. Yeah, because we are seeing that the derivative of cos is negative sine. So just add a negative, then write the cos plus what? Plus a c. Yeah, so the main thing I want to do here is to introduce numerical methods for evaluating definite integrals. It's like an approximation that we can use, an alternative choice or method that is used to get the same thing whenever we're given to evaluate a limit within an integral of a function within certain limits, like AB. So it's like a summation of all the possible changes you ever experience over a curve between a certain interval. Okay, so the main goal that I wanted us to do is to look at certain ways that are used to analyze definite integrals. This is simply under the applications. We're going to look at three methods. There's the midpoint rule, the trapezoidal rule, and we have the Simpson's rule. So the midpoint rule is where we are going to break down the whole summation of your interval. So it's like they give you an area, right, under a curve. Let's say this is our curve. Let's say our curve looks like this. So we're going to demarcate the curve into n particular intervals. So we have n regions or areas. Then we'll be looking for the middle points of each area that is given and sum them all up. That is going to give us an approximation of the integral we need for that curve in between two particular points. So I'll give you an illustration here. Yeah, so if you have so this is the midpoint rule. Yeah, we have certain notations that you have to learn. So if you have, let's say, the integral of b to a, these are the two limits that we are having. We are trying to integrate this. So we say the value of this, or the area of the curve under these 2 points, is approximately the same as the midpoint, the summation of all the midpoints that are needed. So we say from n intervals where I starts from 1, we just sum up the function at those midpoints multiplied by the change, or rather the difference that you are going to experience, where, so I want you to get this, where the delta x is simply b minus a over n. It's like the width of each interval that you are given, width of each interval. Then we have our x, this x bar I is the midpoint. This is the midpoint of the ith interval, so to say. Yeah, so this is like the midpoint. It's just given by anything plus anything before, like the first reading that you get added with the most recent one, or the new one, the bigger one, then divided by 2. Maybe let me give you an example. You see how we apply the midpoint rule. So we're saying, can you integrate 0x squared dx using the midpoint rule when n is equal to, our n is equal to 6 in this case. Yeah, so n has to be given to you for you to get the correct answer. So if it's a question, they'll have to give you the n so that everyone gets the same approximation. Yeah, so if we're looking for n sub-intervals to make under this curve that we have, we're going to get the difference first. We're going to get our delta x. Our delta x is the same as the b, the upper limit minus the lower limit, divided by the number of intervals. So this will be 3 minus 0 over 6. This gives us 0.5. That's the delta x. That will be the width we expect for each sub-interval that we're going to make. That's the delta x. Then, so the sub-intervals are going to be as follows. We're going to get the following, guys, the readings. So the first one, which is 0, because we're moving from 0 to 3, right? So we have 0, each width will be 0.5, so meaning we have 0.5 there. That's the first point. The next point would have been 0.5 to 1. That's the next point. The next one will be 1 to 1.5, because the difference has to be 0.5 in each case. Then the next one will be 1.5 and a 2. Then the other guy will be a 2 and comma a 2.5. Then the last one would be a 2.5 and a 3. So hope you're able to follow up to this point. Then we're going to get the x bar for each particular point. Yeah, so the x bar is very, very, very simple. So like x bar for this guy will be, we'll just sum up this 0 plus 0.5, then divide by 2. Same applies here, x bar again. So we call this x bar 1. This is x bar 2. Yeah, this is 0.5 plus 1, then over 2. This is x bar 3. This is 1 plus 1.5. Then we divide by 2. This is x bar 4. 1.5 plus 2, then over 2. This is x bar 5, 2 plus 2.5 over 2. Then have x bar 6. This is 2.5 plus 3 over 2. Yeah, then this is going to give us a summation here. When you do the punching, you should get something like a 0.25. This is a 0.75. This is a 1.25. Then this guy here is a 1.75. Then here we get a 2.25. The last one gives you a 2.75. Then we need to get the summation of this. Yeah, so we're going to get the function at these points rather. Yeah, so we have the function at each of the points, the midpoints. Yeah, so the function at this, so we are going to have 0.25 to the power 2. The same applies to this again. We do the same. Yeah, so I'll just show it here nicely so that I don't write things. I'll just say we need to get f of x bar for each one of these values. So like square these. If the function was cubed, we would have cubed all of them, because we're putting this in the function. That gives you 0.065. This gives you something like 0.5625. This gives you 1.5625. This here gives you a 3.0625. This here gives a 5.0625. And lastly, you get your 7.56. I have a 25 at the end. Yeah, so what we need is simply a summation of all these values here. So we'll say our area for the 6 intervals is just the delta x that we have and the summation of all the f of x bar that we got from the first one until the last one, which is the 6th one. So we have the delta x is 0.5. That is what we got. Then we're going to sum up all these, right? We sum them up, we sum them up, we sum them up. Yeah, so if you sum them up, you're simply going to get everything here gives you what, a 17.875. Multiply with 0.5, it gives you 8.9375. This is an approximation, but then yeah, this is what you're going to get as the area. You put units squared. So this is how the midpoint rule works. Yeah, this is how the midpoint rule works. Then if you wanted to use the same thing for the same formula, we use the trapezoid rule. So case 2. So this is the formula that we are always going to be using. Yeah, so in simpler terms, we're saying the integral of a definite integral is just half the summation of each part multiplied by the interval divided by the number of intervals that you are given. So let me just show you an example here. You understand it better with an illustration. So the same example that we're from doing previously, I'll use the trapezoid rule to solve it again. Yeah, so 30, this is x squared dx, so that you just notice the difference. The interval given here, our a and our b, are equal to, there's a 0 to 3, that's what we're having. N was given as 6. Yeah, that's what we have. The function is x squared. So again, we get the delta x. The delta x will still be the same. That's 3 minus 0 in this case. Then we have 6. It's just 0.5. Then we need what we call the evaluation points. Yeah, the evaluation points. So we're going to have the usage. We just use the endpoints of each sub-interval. Remember how we said we listed them previously? Remember what we did? We listed them down here. We said these are simply going to be the sub-intervals that we'll be looking at, these guys here. Yeah. So the trapezoidal rule just focuses on the last points. It doesn't use both, like how the midpoint rule is doing, adding them, dividing by 2. But here, we're just going to be focusing on the last points, which are these guys, these values alone. That's what we'll be interested in. Yeah, so there's the first one. Yeah, so we can either use the first ones or the last ones. It's up to you. So here, let's try to use the first ones. We use the first ones. Yeah, let's use the 0. So we'll use a 0. I'll use 0 because they're smaller numbers. It's okay even if you use the last ones, but we can just choose the smaller ones, the first ones, because they're very, very small. they're better. Yeah, so if we have what we can use the same, let's say the endpoints. So we say this, we say use endpoints. Okay, let's stick to endpoints. So the endpoints would have been, the first one would give you what? The first one is 0. The second one would give you a 0.5. Then you have, this is like the starting point. Then the other one will give you 1, and so on and so forth. So the last one, the 60th point, will give you a 3. That's where we're ending from. Then once you get this, we're going to plug each of these endpoints of the sub-intervals in the original function. So we're going to plug them. Yeah, each point, plug it. That's a 0. So you plug them, right? You plug them in the function. You get your answers. Once you are done doing that, we're going to say the formula that we are going to apply is that 3 to 0 x squared dx is the same as, the formula says it's delta x over 2. Then we're going to have the summation of, we say, so it's a sequence, yeah, that has a 2. Yeah, we just say f of x0, the first guy, plus there's a 2, f of x1, then plus, and so on and so forth. So if you notice here, they are going to be repeating outcomes, like this part and this part. So that's where the 2 is coming from. Yeah, so that's the reason why you see the 2. Yeah, this is the final formula for the, yeah, for the trapezoidal rule. So that's the one that we're going to be replacing in. Yeah, so there's a 2 throughout. Only the first term and the last term don't have a 2 in front, but the middle terms all have a 2. So this is where all the 2's are going to be coming from. And if we do that, the delta x was 0.5 over 2. So the numbers that we got here were supposed to be a 0, then a 2 and a 0.25, then plus a 2 and a 1, plus a 2 and a 2.25, and a 2 and a 4, then a plus a 2 and a 6.25. The last one is just 9. Yeah, so if you sum them up and divide by this, the approximation here that you're going to get from what I'm getting here in my calculation should be a 9.125. You notice there's no much difference between this guy and the midpoint rule. Yeah, the Simpson rule is not really important to know, sort of. For you guys, just focus on these two rules, especially the trapezoid rule. This is what you need to know by heart. And if I may, let me just give you a task to just see if you're following. Can you use the midpoint, both the midpoint rule and the trapezoidal rule, yeah, and the T rule, to just evaluate the integral, of this guy when n is equal to 5. So submit this for me. Send me this to see what you're going to get, to see if you follow through what we've done so far. Yeah, thank you so much for watching.